Flying in the United States has increasingly come to feel like a slow bleed on both time and patience. The average traveller has learned to add extra hours into their schedule just to account for the delays and unpredictability of modern air travel. You arrive at the airport early, navigate through long security lines, and then rush across sprawling terminals to catch connecting flights at distant gates. Even then, you might find yourself sitting on the runway through temporary maintenance holds, only to still arrive late at your destination. This is not some rare occurrence or an unlucky one-off event. It is a trend that has become deeply embedded in the system. In 2023, nearly 1 in every 5 flights missed its scheduled arrival time, leaving passengers frustrated and exhausted. Meanwhile, airfares remain stubbornly high because fuel costs continue to bite into the balance sheets of airlines, consuming roughly 30% of their operating expenses. To make up the difference, carriers pile on add-ons and fees, making travel not only more stressful but more expensive. The reality is that the old aviation system is becoming more complex, more costly, and less rewarding for everyday travellers who just want a reliable way to move from one place to another. Against this backdrop, a very different thread begins to emerge, one that promises not only change but disruption. Enter the Tesla super electric plane, a groundbreaking $79,979 electric aircraft that aims to apply Tesla's electric vehicle, a philosophy to the skies. This is not a concept confined to sketches on a whiteboard. The design is paired with a detailed production plan that makes use of modular airframe pieces, shared battery packs, battery management systems, BMS, motors, inverters, over-the-air update, OTA support, and a robust service network. Beyond the technical innovations, the rollout strategy also contemplates factory choices and charging infrastructure in a way that highlights Tesla's practical mindset about cost control and uptime. As we dive into this project, we test what it could mean, not only for the aviation industry, but for the daily user experience of flight. Now, if you are interested in following these kinds of clear, data-backed breakdowns, the request is simple. Subscribe to westtech and join over 219,743 subscribers who are already keeping up with the channel. Turn on that notification bell so you never miss an episode. With that said, let us begin by exploring the first key question. How will Tesla cut cost and accelerate production for the super electric plane? Tesla's foundation for production lies in its Gigafactory system, a series of massive, highly automated plants optimized for modular assembly with rigorous quality assurance. These facilities are not just large warehouses, they are ecosystems of robotics, streamlined workflows, and data-driven inspections. When that philosophy is applied to light aviation, the results are striking. The major assemblies of the Tesla super electric plane, such as the fuselage, wings, battery pack, motor, and power electronics, can be standardized into large modules. Each module undergoes its own inspection routine before being joined in a cell line-style final assembly. The reduction in the number of joints, combined with clear test criteria at each step, drives down both production costs and defect rates. At the same time, it improves repeatability, which is critical when scaling up output. In simple terms, the fewer the connections, the lower the risk of flaws, and the faster the product moves through the assembly line. This modular mindset also helps answer the question of where production should take place. Gigatexas, with its immense space and infrastructure designed to handle oversized structures, stands out as the natural candidate for airframe work and final assembly. Already home to large body projects in Tesla's automotive division, the site is primed to extend its expertise to aircraft. Once the airframe is manufactured to tight tolerances, the plane moves through modular stations similar to Tesla's automotive production lines, keeping schedules stable even as workloads grow. Meanwhile, the energy modules tie directly into Giga Nevada, known as Tesla's battery hub. This facility already manages the cell packs, BMS units, and pre-processing for energy modules. By standardizing the battery pack, BMS, and inverter into a single, independently tested energy block, the airplane plant only needs to receive compliant modules and install them into the airframe. This shortens wait times at the factory, stabilizes output quality, and lowers inventory costs because the platform is shared with Tesla's existing EV business. Looking outward, the global market underscores the importance of Berlin and Shanghai. Both gigafactories have already demonstrated the ability to localize rapidly, establish efficient supply chains, and sustain high output with a consistent cadence. When the Tesla super electric plane expands into Europe or Asia, transferring the modular process to Berlin or Shanghai trims logistics costs for bulky components and accelerates delivery to customers. Furthermore, a multi-continent footprint enhances supply chain resilience, ensuring that production can be rebalanced if one site encounters disruption. All of these decisions add up to a simple but powerful chain of cause and effect. Modular production reduces part count and joints, which cuts defects and accelerates assembly. Faster assembly allows a factory to process more units in the same time frame, reducing average unit cost. Standardized battery, motor, and power electronics modules make inspections and in-service replacements straightforward, which reduces downtime for customers and lowers lifetime maintenance costs. And thanks to the Gigafactory network scale, Tesla achieves granular quality control and ensures parts availability. Each module of the Tesla super electric plane comes with traceable ID, test records, and common acceptance criteria across sites, ensuring high volume production while keeping quality steady. For users, this translates into a lower total cost of ownership, higher aircraft availability, and a smoother maintenance experience. In short, every link in the chain, from the factory floor to the flight line, serves a singular goal: to make electric aviation practical, not just theoretical. The second question builds directly on this foundation. How will Tesla's powertrain and energy network shape the super electric plane? Tesla's technical expertise in electric vehicles offers a blueprint for light aviation that is both efficient and scalable. At the core lies a standardized stack of battery pack, BMS, motor, and inverter, proven across hundreds of thousands of vehicles each year. This scale is not trivial. It transforms complex systems into repeatable, reliable modules that already have a track record of working in harmony. Efficiency is the first pillar. Tesla's electric cars achieve an overall efficiency of around 87 to 91%, even after accounting for regenerative braking. Modern electric motors frequently run at efficiencies above 90%, meaning far less energy is wasted as heat. Compared with traditional combustion engines, which lose a significant portion of their energy to friction and heat, electric powertrains convert more of their input into useful motion. For a light aircraft, this translates into either extended range or a higher useful payload. Put simply, less energy waste means more flight minutes for every charging minute. Noise and smoothness form the second pillar. Unlike combustion engines that rely on cyclical explosions to generate thrust, electric propulsion avoids those vibrations and sound waves. Instead, most of the audible noise comes from the propeller and the movement of air. For reference, the Pipistrel Velis Electro, a certified electric trainer, registers about 60 decibels during training use, roughly the sound level of a normal conversation. Tesla does not necessarily target that exact number, but it proves what is achievable. When paired with a high-efficiency motor, a finely tuned inverter, and aerodynamically optimized surfaces in Tesla's design style, the super-electric plane can credibly deliver quieter, more pleasant flights, reducing fatigue for both pilots and passengers. The third pillar is energy infrastructure, arguably the most decisive factor in operational feasibility. Tesla's Supercharger V4 network in North America already offers around 325 kW and is expected to climb higher as deployment expands. High-power sites can dramatically shorten turnaround times between flights, especially if Tesla introduces adapters and standardized procedures for aviation use. Where the grid is weak, Tesla's megapacks can function as energy buffers, dumping fast bursts of power into aircraft and then slowly recharging from the grid. On a smaller scale, the Powerwall 3 can support auxiliary loads and scale incrementally. With more than 5,000 public-use airports in the United States, sensible placement of charging infrastructure ensures the super-electric plane can operate efficiently without relying solely on high-capacity grid points. To illustrate, Imagine a battery pack of 200 kWh capacity with an aircraft charging rate of 250 kW. Charging from 10 to 80%, roughly 140 k, would take just over 30 minutes under ideal conditions. While this is not a product promise, it demonstrates how pack size and charging power affect turnaround times. Pair this with the fact that AV owners already spend roughly half as much on maintenance as gasoline car owners due to fewer moving parts, no oil changes, and simplified drivetrains, and the implications become clear. In aviation, where downtime and reliability are critical, a monitored BMS, high-efficiency inverter, and electric motor can reduce both downtime and lifetime maintenance costs. When these elements are combined, the cause and effect chain is straightforward. Higher drivetrain efficiency wastes less energy, high-power charging reduces ground time, and standardized modules with remote diagnostics lower scheduled maintenance needs. Together, these improvements increase flight hours while cutting ownership costs, making the Tesla super electric plane practical for daily use.